Hello learners, I am Sudhir Kumbhar, Assistant Professor of Physical Chemistry, gives you a quick review of photochemistry. Photochemistry is the study of chemical reaction initiated by absorption of energy in the form of light. Term light includes UV visible radiation 2000 to 8000 angstrom. The reaction, which can be brought about by exposing the reaction mixture to the radiation, is known as photochemical reaction. The photochemical reactions are synthesis, decomposition, polymerization, isomeric change, photooxidation and photoreduction. Photochemical reaction involve absorption of light radiations. Presence of light is the primary requirement in photochemical reaction. Photochemical activation is highly selective process. In photochemical reaction, delta G may be positive or negative.
Absorption of light.
When light is fallen on a cuvette containing solution, a part of light transmitted, a part reflected and remaining get absorbed. In photochemistry, I0 is equal to IA plus IT as IR is neglected. Therefore, only absorbed light is considered in photochemistry.
Laws of photochemistry. Draper law.
Only those radiations which are absorbed by a reacting substance or system are responsible for producing chemical change. Thus, only absorption process results photochemical reaction.
Second law is Stark-Einstein law.
Each molecule of absorbing substance absorbs one photon or quantum of the radiation in primary process. This law is also known as law of photochemical equivalence or principle of quantum activation.
The third law is Lambert law.
When a monochromatic radiation is passed through a homogeneous absorbing medium, the rate of decrease in the intensity of radiation with thickness of absorbing medium is directly proportional to the intensity of the incident radiation.
The fourth law, Lambert-Beer's law.
When a beam of monochromatic radiation is passed through a solution of an absorbing substance, the rate of decrease in the intensity of radiation with thickness of absorbing solution is directly proportional to the intensity of the incident radiation and concentration of the solution.
The energy of single photon.
E is equal to h nu, where nu is equal to frequency of absorbing photon and h is the Planck's constant having value 6.624 into 10 raised to minus 34 joule second.
The energy of 1 mole, or Einstein, photon.
E is equal to 1.1962 times 10 raised to 8 divided by lambda in joule per mole.
Transmittance.
I divided by I0 is called as transmittance, which is the fraction of incident light transmitted.
Absorbance.
I0 divided by I is equal to optical density, D or opacity, or absorbance, A. The reciprocal of thickness X, required to reduce the light to 1/10 of its intensity is known as extinction coefficient of absorbing medium. In this equation, A letter is the extinction coefficient.
Molar extinction coefficient.
Molecular extinction coefficient is the optical density when layer of solution has unit thickness and absorbing substance has unit concentration.
Spin orientation and multiplicity.
At normal temperature, almost all molecules are in the ground state. That means all electrons are at ground state. Hence, all electrons in ground state are spin paired. The upward direction electrons with plus half spin and downward electron with minus half spin. So the total spin S is equal to 0, then 2s plus 1 is called spin multiplicity of the energy state. So the spin multiplicity of the ground state become 1. This energy state is known as singlet ground state, designated as S0 as shown in figure A. After absorption of photon of light, the energy is transferred to the electron and goes to excited state. Now, if excited electron has anti-parallel spin, then total spin S is equal to 0. Hence, spin multiplicity of excited state is 1. This excited state is called as first singlet excited state and designated as S1. This can be shown in figure B. Now, if the excited electron has parallel spin with its mate electron, then total spin S is equal to 1 and spin multiplicity of state S is equal to 3. This excited state has spin multiplicity 3, so called as triplet excited state, designated as T. This is shown in figure C. Photosensitization is the process of initiating a reaction through the use of a substance capable of absorbing light and transferring the energy to the desired reactants. Sensitizer is suitable atom or molecule that absorb radiation and pass this absorbed radiation to the reacting molecule. Examples of photosensitized reaction are dissociation of hydrogen and photosynthesis.
Quantum yield or quantum efficiency, phi.
The number of moles of light-absorbing substance that react for each Einstein of radiation absorbed. Or, it is number of molecules of light-absorbing substance that react for each quantum of radiation.
Factors affecting quantum yield.
1. Temperature. Quantum yield increases as temperature increases. 2. Wavelength. Quantum yield increases as wavelength decreases, and vice versa. 3. Light intensity. Quantum yield increases with increase in the intensity of light, and vice versa. 4. Addition of inert gas. Addition of inert gas in photochemical reaction increase the quantum yield.
Chemiluminescence.
The emission of light as a result of chemical reactions at ordinary temperature is called chemiluminescence or also known cold light. The best known example of chemiluminescence is the light emitted by firefly.
Electroluminescence.
Electroluminescence is the phenomenon where a material emits light when electricity is passed through it. The best known example of electroluminescence is the neon light.
Bioluminescence.
Bioluminescence is the phenomenon of production of light in a living organism as a result of energy released from chemical reaction occurring inside the organism. Best known example of bioluminescence is the fish live in the dark environment below 200 meters in the ocean.
Photophysical processes and photochemical processes.
Fluorescence and phosphorescence, two phenomena emit radiation during de-excitation, are called photophysical processes. During de-excitations, excited electron returns to normal state after producing some chemical change is called photochemical processes.
Jablonski Diagram.
Alexander Jablonski, a Polish scientist, developed a method to represent various processes occurring due to absorption of photon from visible spectrum of light by particular molecule. This schematic pictorial representation is called as Jablonski diagram. In this Jablonski diagram, first transition is always absorption of light. The vibrational relaxation, internal conversion, and inter-system crossing are called non-radiated transition. Fluorescence and phosphorescence are the radiative transition.
Fluorescence.
The transition in which molecule loses its energy from singlet excited state to the singlet ground state by means of an emitting radiations is called fluorescence.
Phosphorescence.
The transition in which molecule loses its energy from triplet excited state to the singlet ground state by means of an emitting radiation is called phosphorescence.
Time scale for radiative and non-radiative transitions.